nanohub.org.
Online simulation and more for nanotechnology.
Okay, so I just want to first of all thank everybody for being here. Also, thanks to everyone that I've gotten a chance to meet. I have been very much impressed and excited that Purdue was everything that I had been hoping for when I decided to kind of, on some level, start over after spending 12 years at Sandia National Labs in Albuquerque. And so what I want to talk today about, and really what my mission in this seminar is today, is really twofold. It's a little bit different than a classic seminar, than something that I would typically get.
Workshop, presentation. This is not a workshop. The presentation. I just want to be clear with you that our office will help you with all the kinds of Graphene.
Is anybody else getting some feedback here, or is it just me?
Someone else is playing something.
Oh, okay. So I just wanted to say that I really have two kind of goals in this presentation. And so number one, what I want to do is really introduce myself and kind of some of the things we think about and some of the tools we're bringing on. And then number two, explain more what I'm planning to do while I'm here rather than what I have done in the past. Although we'll talk a little bit about what I've done as a way that it sets up what I want to do. But really, one of the reasons I'm here is to collaborate, to leverage the resources of kind of the Purdue scientific community in general, and really one of the things I think that is a strength of our group at Sandia, and what I hope to establish here, is the fact that we're a group that really likes to take on problems from all different sorts of physics and kind of play around with them. So today what I'm going to be talking about is taking a concept from thermal transport and nanophotonics and really explain how we're going to put them together. So to do that, let me just really tell you where I'm speaking from and where I'm coming from. And so our group really focuses on kind of four core areas. I was trained in my doctoral studies as a Raman spectroscopist, so I very much enjoy vibrational spectroscopy. But I also was trained in a group that did thermal physics. And so we've continued to think about, why does heat move? What are the mechanisms that drives heat transport? And then as I went to Sandia, we moved and really began to think about 2D solids. So graphene, the TMDs, and van der Waals solids in general, in the context of nanophotonics. And so when you put that all together, really what our group does is we're a photon group and a phonon group. And specifically, you might say, well, that's a little bit different, that those don't seem to go together, but they really go together on two accounts. The first is the fact that we really think about infrared photons a lot. And so infrared photons have energies that are on the same scale as, on the same energy scale as phonons, specifically optical phonons. And then in polar materials, those phonons can very much interact with infrared photons to create these things called Polaritons. And so we're going to spend most of our day today speaking about Polaritons, which are kind of a hybrid between a photon or a light particle in some material dipole. And so if we kind of put this all together, I like to really say that we're really a Polariton group. And so that's the way we're going to approach this problem. And so let me tell you what the problem is. So as we think about kind of modern microelectronics, Moore's law, even though we keep continuing to believe that it's going to stop, and it will stop, and on some level it's already kind of stopped or slowed down, there is always going to be a push to get more capability in smaller spaces. And more capability means that there's more energy. And the second law says that if you have more energy and more work being done, you're going to have more heat. And so if we want to make it smaller, that means heat fluxes get higher. And there's a problem. Those heat fluxes have to move and get away from whatever's operating to make sure that we don't have diffusion, we don't have other failure mechanisms. And as we get smaller and smaller at the submicron and the nanoscale, and in particular at material interfaces, phonon and electrons just become less efficient at moving energy. It's kind of like a clown car problem. You have a bunch of things in a small area, and so everything becomes inefficient. So that's a problem that's been well known. People have been working on this for decades. But where I think we're a little bit different is that rather than trying to make phonons and electrons better at moving through small spaces, I'm going to posit that we need a fundamentally different energy carrier. And specifically, I believe that polaritons are that carrier. And I believe that because polaritons, as they get smaller, actually become more efficient at moving heat, and I'll show this. The other thing that we really get excited about polaritons is since they have this photonic character, we can leverage all the links and ways that we know to modify light in terms of metasurfaces and metamaterials and actually change their dispersion. Whereas in contrast, for things like electrons and phonons, we conceptually know how to change their dispersions, but doing so in reality is very, very difficult. And then finally, if we take these polaritons and put in some material that has a plasmonic character, those plasmons are, of course, related to free charge. And so we can electrostatically gate it and move those plasmon polaritons. And thus, not only can we engineer the dispersion, but we can actually turn it on and off and effectively hit a button and change our response. And so that's where we're going today. I want to explain to you that phonons and electrons are bad in small places, and that polaritons give us a way of moving heat at the nanoscale that is so characteristic of microelectronics. So let's begin and just make sure that we're starting all at the same place with what I mean when I say a polariton. And so, of course, we all know that a photon is an electromagnetic wave. And so if we just take the E field component of the electromagnetic wave, let's say it's maybe this blue wave here in the top left, we know that effectively that's an AC source, and that AC source has a certain frequency. And so we also know that when we have AC sources at the same frequency and the same momentum, if we think of it from a more quantum perspective, they're going to interact. And so if we want to create light matter interactions, we start to think about, well, what are the other material dipoles that are available to leverage? And so from the nanophotonics community, I would say probably the most popular is obviously the plasmon polaritons. So these are our localized surface plasmon resonances that we use in home health diagnostics and things like that. And then maybe somewhat, maybe not as well utilized as the plasmon polariton is exciton polaritons, where we have this coulombic force between an electron and a hole. But in both cases, we have electronic charge getting sloshed about by the photon at a frequency that allows them to interact, and they create kind of this new energy particle that has aspects of both the plasmon and the photon, or the exciton and the photon, and we can use those to different ends. Now, in the, let's say maybe the last, decade or so, work of J.J. Graphene and Josh Caldwell more recently, really phonon polaritons have taken on kind of a more, have come more to the forefront. And so I think that it makes sense to just talk about why a phonon, which is a vibration, might also act like an AC source. So down here on the bottom, I'm showing a perovskite unit cell, and it doesn't have to be a perovskite. Anything that is polar will do. But we can think about the fact that a vibration means that atoms are going to be moving. And so there will be certain vibrations where cation ions could move in a direction opposite to the anions. You're seeing the up arrows and the down arrows. And so if we think about that, we've got a positive charge and a negative charge that are going back and forth at some frequency. That's an AC source. Same energy, same frequency, same momentum, quantum carriers will respond. And so we have a phonon polariton. And phonons scatter at have a much longer lifetime, and so they can be much sharper, and we can create very, very sharp resonances for us. And we also know that from thermal transport, sharp resonances, longer lifetimes are good things. So since heat is moved by phonons, and since phonon polaritons have these long lifetimes, we might think to ourselves, could this be useful to move heat? And so for quite a long time, we've known this from the perspective of radiation. So some work from J.J. Grafet's group in 2001 that I'm showing up here in the top left-hand corner shows that as you get two surfaces very, very close to each other, so submicron again, that the radiation, the heat transport due to radiation far exceeds the black body limit. And this is something that if you look at Planck's original paper, it's an okay thing. There's some assumptions for that far field value. And so that makes sense. And it's been demonstrated experimentally again and again. And so not only is it just near field heat transport in general, but in particular to phonon polaritons, Pramod Reddy's group at the University of Michigan showed a few years ago that you could very much enhance near field conductance. And this is what I'm showing from one of his papers in the bottom left-hand corner. If you coated your two surfaces with phonon polaritons that like to talk to each other. And so the message you should be getting is that from a radiation perspective, we know that phonon polaritons can be useful. But maybe what's not as self-apparent or self-intuitive is the fact that phonon polaritons can also operate in a quasi-conduction mode. And so what I mean by this is that they can actually move heat along a surface rather than just normal to that surface. So think about the fact that if I have a surface in radiation, the heat is moving perpendicular to that surface. Here, when I'm talking about polariton conduction, it's moving parallel to that surface. And really this work was kicked off by Gong Chen's group at MIT in the early 2000s, where he showed, as I'm showing up here in the right-hand corner, that you have, as you get down to about 10 microns, or even 50, as you get to these submicron levels, the phonon polariton is actually carrying more heat than the phonons within SiO2. And so as you get to these kind of hundreds of nanometers levels, the phonon polariton's actually carrying more energy than the phonons themselves. And I just want to say up front that you do not need to shine light to get these polaritons to move in this conductive mode. Fluctuation, dissipation, and heat gradients in general, or temperature gradients, I should say, rather than heat gradients, suffice it to kick off these polaritons. And so this was a theory for quite some time. And then it was added on to by Sebastian Vos's group in France. And then in the last year and a half or so, there's been about 2 or 3 experimental demonstrations of this. One by Jean-François Bijou's group here in the Burke Center that I'm showing under in this bottom right-hand plot, where he showed that in hexagonal boron nitride that as the temperature increased, the thermal conductivity went up in a crystal. And that is absolutely not what you would expect. And he explained that by invoking this kind of idea of a polaritonic mechanism. Sebastian Voll's group did something very similar in SiO2. And so this theoretical idea of polariton conduction has kind of moved from a theoretical perspective into more of a reality. And I think that we're at very much at kind of the nascent portion of this kind of vein of research. And I think there's quite a bit of opportunity. So I want to explain why I think there's this opportunity. And the way that I want to do that is really to explain some fundamental advantages that phonon polaritons have over just typical phonons when we think about nanoscale thermal transport. So the first thing that we can think about is that polaritons have dispersions that are very, very different than phonons. And so I'm plotting a graphene plasma polariton here in red and a gallium nitride, just normal phonon dispersion in blue. And there's a couple of things you should see. Number one, the polariton has much steeper dispersion. That means that you have a very high group velocity, good for moving energy. And second, it can get to quite high energies over that which we can see in phonon environments. So we have high energy and we have fast particles. That's good for transport. But really the things that get me most excited are when we think about what the kind of constitutive relationships are for controlling these quantum energy particles. And so I like to think of it as Maxwell kind of looming over Newton. And so let me explain what I mean by that. Newton is really F equals ma, of course. And so that's really what a phonon dispersion comes from. If we think about a solid as being connected with a bunch of balls and springs, we get a dispersion relationship. And so it's really the periodicity of atomic nuclei that give us that dispersion. So if we want to change the dispersion, we need to change atomic nuclei and their bonding. We can do that, but that really asks us, if we want to do that in a very deft fashion, that really requires us to go ahead and fabricate and change at the atomic level. That's difficult. When we think about working with polaritons, we're really working with the photonic part of the particle. And so that allows us to leverage what we know from metasurfaces and to work with the wavelengths of those polaritons, which can be in the infrared. And so if we want to make metasurfaces and things, that means that we're now fabricating at hundreds or maybe, at the smallest tens of nanometers. And so that is much more doable. And so that allows us to actually truly create the dispersion, which we can't really do with phonons by themselves. And then we get a couple of other bonus things. And that is, first of all, that of course, polaritons love interfaces. Normal energy carriers, phonons and electrons, when they see an interface, bang off of it. Polaritons, if we design them correctly, kind of skate along them. And so I like to think of them as being an interface file. They like interfaces, whereas phonons don't. And then, as I already mentioned, we can tune them if there's any sort of electronic component to it, like in a graphene plasma that I'm showing here. We can electrostatically gate it and change those properties and change the dispersion. So we have something that's high energy, it's fast, we can change its dispersion to suit our ends, it likes interfaces, it's dynamically tunable. We see net advantages. Now what I want to do is I want to show you that what we're doing right now from a nanoscale thermal transport perspective just doesn't work. And it doesn't work because the solutions aren't scaling. So the idea of thermal dissipation in microelectronics is not a new problem. It has been being pursued and thought about for quite some time. And of course, Purdue has been one of the leaders of that field for pretty much the extent of the topic. But I'm going to say that while that work continues to be necessary and while that work continues to be very innovative, that other approaches need to be thought about as well. And because if I want to oversimplify what our approach as a thermal physics community has really been, found a problem, she just wanted to throw cold at it. And so what we've done is tried to make, we're now putting water in our data centers, we're putting water in our computers, we're thinking about water everywhere. And so the question is there a solid state physics perspective? But that brings us to a kind of a general problem. And so what I'm doing right now is I am showing just kind of a very generic electronic package and really tracking DARPA programs over about the past decade and a half. And so DARPA in 2007, 2008 was really working down here at the bottom, kind of on the thermal ground plane and these fins. And so if we think about it, that's far away from what's actually getting hot, which is this red chip right here. And they're big. Those things you can physically hold in your hands pretty easily. And so those programs were successful. They increased our cooling capabilities, but they just didn't get us as far as we would like to go. And so in about 2009 timeframe, DARPA said, let's get closer to where the chip is actually getting hotter, and let's make better thermal interface materials. And so this was this NTI program. And so now we've gone from something that's big that you pick up with your hands to something that you really pick up with your tweezers, a very thin fin. And then 2010, 2012, we said, let's get even closer. Let's actually get on the chip to cool it. And so there was the near junction thermal transport program and the ice cool program, which if I want to be oversimplistic, I can explain as let's wrap everything in diamond. That's good, but not good enough. And then let's wrap everything in diamond and then shoot water in diamond heat sinks to increase cooling. So all of those things work. But there are certain places that are obviously not going to be keen on putting diamond around everything and are not going to be keen on pushing water through the chips themselves. And I would say that one of the reasons that we've gone to these such great extents is that we've really begun to go up against a basic length scale limit. And that is the fact that our thermal solutions, what we want to carry heat, are very much approaching the mean free paths of the phonons that are carrying the heat themselves. And so really, how do you make something to enhance heat transport when it's a size that's on the scale of what's actually carrying the heat's mean free path? So there's a problem. We need to do something different. And so I want to show you that this is just a general problem, because not only do we need solutions closer to the source, if that's the case, they got to get smaller. And so getting smaller means they're going to get worse, even though we need them to get better. And so it's paradoxical. And it's not just a problem specific to one material. It's a problem that's specific to materials in general. And so to kind of explain that, let's just look at the Phonon gas model, which is kind of our first cut way of thinking about thermal transport. So this is a little bit of a hairy equation, but let me just explain what you should be looking at. So really what we're going to do is we're going to count all the heat carriers. So that's the summation. We're going to count how much energy they have. This is our statistics to make sure we're counting the right number, and then how fast they're moving, and then the extra velocity times the scattering time gives us the mean free path. So the dispersion tells us how many carriers we have and how much they're moving, and then this tau term on the right tells us how soon they scatter. And so when we think about it in this kind of somewhat simplistic perspective, and we say, how can I make the thermal conductivity bigger? Normally, the way that we go about that is we say, well, let's get rid of the bad stuff. And so the bad stuff can be impurities, things that shouldn't be in the material, but just get in there because life is reality rather than an ideal system. Or the fact that as we're growing it, it just doesn't grow perfect and we have dislocations. And then where we've really been thinking about things quite a bit lately is how do size effects change things? So if I make my layer smaller and smaller, how much does that affect thermal conductivity? And so one of the questions that I like to ask people is, if you had a magic wand and you could do anything to your material, would you get rid of the bad stuff, or would you just somehow be able to always keep it relatively large? And when I say large, I mean more than a micron in kind of its smallest spatial dimension. And so this problem really kind of caught my attention when we were looking at gallium nitride. And so gallium nitride, of course, is used in quite a bit of applications commercially already for communications, radar, things like that. But it's becoming more and more prevalent along with its alloys in power electronics. And so in these power electronics, when you kind of try to justify the use of gallium nitride and think about it, one of the things that you always want to say is that it has a high thermal conductivity. Its textbook value is about 250 watts per meter K. And this has been known since about the 80s, late 70s, early 80s, that it's a high thermal conductivity material, about 1.5 that of silicon. And so my question was, well, what happens to gallium nitride's thermal conductivity when I actually put it in one of these power devices? And so my naive thought was that, well, we're going to dope these to relatively high levels, and dopants will very much hurt the thermal conductivity. And so I had a collaborator, Andy Allerman at Sandia National Labs, make this gallium nitride. And he made a series of samples where he changed the dopant concentration, both in N-type and P-type material. And the P-type material really showed us exactly what we would expect. We put more dopants in, more impurities, the thermal conductivity goes down. But the N-type material showed no sensitivity to the impurity. And so we were doing the time domain thermal reflectance measurements. We thought we were doing them wrong. We got more samples. We sent the samples to Patrick Hopkins' group at the University of Virginia. He did a blind test, and all the experiments came back equal to one another within the uncertainty. And so now we had to explain the physics of what was going on. And so we kind of used this, this villain kind of perspective to kind of really think about, well, what is our villain here? And so we did some X-ray analysis, XRD analysis, some cathodoluminescence, and our dislocation densities. We obviously knew that our impurities weren't affecting things when it came to the thermal conductivity for the N-type material. And so that couldn't be it. And so the question becomes, well, is it the dislocations or is it these size effects? And so what I'm plotting here is a calculation from the Phonon gas model of the thermal conductivity versus dislocations here on the left, and the thermal conductivity versus the thickness of the gallium nitride layer here on the right. And so, as I alluded to mistakenly in the last slide, we did cathode luminescence, we did XRD, and we knew that our dislocation density was below 10 to the 8th. And so dislocations weren't really having an effect. But when we looked at this Phonon gas model, we see that right at about 1 micron of thickness, the thermal conductivity has dropped by a factor of 2. And so this is just due to the fact that phonons that would go farther are scattering before they normally would because they're running into an interface. And so the question becomes, well, has anybody ever seen this before? And so we plotted the thermal conductivity as a function of thickness for about every gallium nitride publication that I could find since people started reporting the thermal conductivity of gallium nitride. And so that's what all those black dots are. And then the things that I showed earlier are these filled modes. And so you see that in general, very rarely do we get materials that have a thermal conductivity close to this textbook value of like 237 watts per meter K. And also in general, as your thickness goes up, your thermal conductivity goes up. And that is because what is carrying the heat, so if we look at the dispersion here, when it's a bright color, that tells us that it's carrying more heat relative to its friends. And so we see that in the bulk, these kind of long wavelength acoustic modes, which we know are the big heat carriers, are able to carry quite a bit of heat. However, when we go to 1 micron, those are now banging against the interface. See, it turned blue. And so that's no longer the dominant heat carrier. And so at the end of the day, the message, if you're thinking about devices, is that you're not going to get that textbook thermal conductivity, so don't put it in your model. And then on the other side of the coin, the other thing to realize is that although all our devices are going down in size, our ability to move heat is also going down when we really need it to go up because the heat fluxes are increasing. And so I just want to kind of explain that polaritons scale in the opposite direction. And so to show that, I am plotting here 2 different sets of curves. So the dotted lines up here are the thermal conductivity of silicon as a function of film thickness at room temperature 500 and 700 K. As the film thickness increases, the thermal conductivity of the silicon phonon increases. And as the temperature increases, the thermal conductivity of the silicon phonon decreases. Now, the solid lines are a calculation of the SiO2 surface phonon polariton. So remember, SiO2 from a phonon perspective is glass. It's an insulator. And so this is it has a thermal conductivity down at 1. Notice also that this is a logarithmic scale. And so the first thing you should see is that we actually have an opposite trend. As the film thickness gets smaller and smaller, the thermal conductivity of this SiO2 polariton gets bigger. And also as the temperature goes up, like it would in an operating microelectronic device, the polariton thermal conductivity goes up as well on some level. And not only that, we've now taken what is typically a thermal insulator and made it equivalent to a decent thermal conductor, where we have these intersections. So at high temperature, at 500 K here, we're seeing a crossover between a thermal insulator with a thermal conductor at about 20 nanometers. If we compare it to the Phonon and SiO2 by itself, it moves up to about 100 nanometers. So message number one is that Polaritons scale in the way that we want them to scale to move heat in these nanoscale electronics. And so that is one of the reasons, from kind of a more thermal perspective rather than a dispersion perspective, why we're so excited about them. The other reason is because in heat transport, interfaces are everywhere and they're bad. Interfaces slow down heat transport. We know this. When you walk down the hall, you can walk down the hall quickly. You get to stairs, you slow down. If you're just turning from one direction to another at an intersection, you slow down. The metaphor might be a little bit stretched here, but the message is that you can have two perfectly bonded materials and the heat is going to feel a resistance as it moves from it. And when we think of kind of modern day microelectronics, interfaces are everywhere. Intel's memory that I'm showing here in cross section, you can see all the horizontal lines are interfaces. A gallium nitride hemp, the false color SEM at the bottom left, those are all interfaces. And notice the length scales of the different layers. And then in the ultimate limit, if we think about 2D materials, we have interfaces everywhere. And from a thermal perspective, they're bad. And what I mean by that is we can take the thermal resistance or the Kapitsa resistance of an interface and make it equal to the same thermal resistance for a given thickness of SiO2. And you see here that within the normal range of phonons, our SiO2 equivalent thickness ranges from on the order of 2 or 3 nanometers all the way up to tens of nanometers. And so if you would think about designing a device where you had problems with heat transport and you suggested putting in a couple extra 100 nanometers of, or a couple, 50 nanometers of SiO2, everybody would look at you crazy. And so we don't like these interfaces. And not only that, from a kind of basic physics perspective, they still kind of confound us. And so I'm going to ask a question right now, just to really let you think about it. And what I mean by that is, are interfaces good for heat transport or bad for heat transport? I've already said they're bad. But if I have a perfect interface, is that better? Or if I have a disordered interface, is that better? And the answer that you came up with in your head, I have good news and bad news. The good news is you're right, and the bad news is you're wrong, regardless of what you picked. And so what I mean by that is, at least my intuitive thought was that the thermal boundary conductance would go down as you had disorder, right? Disorder is typically bad for transport. And so we've seen that in systems, but we've also seen that if we purposely disorder the right systems, we can also make it good. And so at the end of the day, there's questions on basically how do we think about interfacial thermal transport? There's also questions about even what modes are moving that heat transport across the interface. And so what I would like to posit is that there's a possibility for actually doing some sort of bridging in the energy transport modes by taking, so for instance, if we have gold on top of diamond, I'm showing the normalized densities of states for gold and diamond here in yellow and blue. And we look at the polariton that forms between them. you see that we get this plasma polariton that in effect bridges the two samples or the two materials. And so the question is, could we use that as a way of moving heat? On some level, we can think of this as the limit to near field heat transport, where the layers are not separated by vacuum, but are actually touching each other. And so I think there's promise here, not just because of kind of this idea from a density of states perspective, but also when we think about how we design a lot of our metasurface systems here. So this is some work that we did a few years ago, where we made a tunable infrared reflector out of the ferroelectric lead zirconate titanate. And so down there in the middle right here, I'm showing kind of the resonance that we are focused on. And then we would pull the ferroelectric and we could show that we could tune it to some level. And then if we looked at it as a function of the electric field that we put across it, we could see this nice butterfly loop that is characteristic of a ferroelectric. And what's kind of nice about a ferroelectric, of course, is there's different polarization states. And so we could use its remnant polarization to actually have it live in two different states that would latch. But for the purpose of our discussion, why I'm excited about it is because while this looks like a grating, it didn't actually operate like a diffractive grating, but more like a metal insulator metal waveguide. And so when we look at the field profiles within this material, when we're off of resonance, nothing is really happening because we're off of resonance. But at resonance, you clearly see the formation of this resonance here, where we've effectively got an enhanced field such that the top interface is talking to the bottom interface. Okay. And so if we think about that from the perspective of thermal transport, what we're really saying, of course, is that we have a gap plasma polariton. Like that's what we call it in nanophotonics. And so my question is, can those gap plasma polaritons actually be utilized to couple these boundaries to move heat from material 1 to material 2? And so that's the question. Those are the things that we want to go ahead and pursue. All right, so let's just kind of recap here real quick. So I've told you that phonons and electrons are not great in small spaces. I've tried to posit that polaritons give us a different perspective. And one of the things that I told you is that dispersion engineering of polaritons is doable. And I haven't really given a whole lot of evidence for that. So I want to take a step back and give some evidence for why we always are engineering the dispersion of polaritons in the nanophotonics community. And so we can use those same concepts and just apply that to thermal transport. I just want to say that I am going to talk about graphene. And I know that graphene, while, about 10 years ago, it was the wonder material and we had all this breathless kind of media attention. I still think it's useful. I don't think it's useful because it's the hot material anymore. I think it's useful because it has a two-dimensional density of states that allows me to change its optical properties quite a bit. It's flexible, so I can put it on almost anything, and so I can do heterogeneous integration with it. That's why I like graphene. So I think it's useful to at least justify when we're using one of these materials. And so we did quite a bit of work on using graphene to make tunable infrared reflective filters. And so what I mean by tunable is not that we made it tunable by changing the metasurface, which in this case is really, really boring. It is just a grating. But by actually putting a gate voltage from this top contact to this bottom contact. And when we did this, this is experimental data, the FTIR spectra changes quite a bit. But I want to just kind of point out that in this case, we had SiO2 sitting underneath the graphene. And then we changed this device and actually put down a hafnia layer underneath it. And you see that our plasma and polariton response changes quite a bit. We still have a change in the reflectance as we put the gate voltage across it, but the whole spectrum has changed quite a bit. And that's all because we changed the plasmon phonon polariton dispersion. As the graphene plasmon and kind of the Rastlalin bands of these materials, or the phonons in these materials, hybridize, we're actually changing the entire plasmon phonon polariton dispersion. And we don't really think about it that way. We just think about it typically in optics as, well, I changed the optical properties. But what we've really done is change a dispersion. And so we should be able to apply that to thermal transport. The other thing that I told you that Polaritons could do is become push button. And so what I mean by that is that you can put a dynamic dispersion onto something. And so what I'm plotting here on the left are some calculations that a postdoc in my group, Amon Jarzembski, did, where he calculated how the rate of tuning changes as I move the Fermi level on graphene when it sits atop different dielectrics. And you can see if we're sitting on vacuum versus sitting on SiO2, the tuning changes. And so that gives us a way of kind of changing how much or the dynamic range of our tuning. And then we actually made one of these filters directly on top of a superlattice infrared detector and showed that we could change its spectral response. So it was a fully integrated graphene filter atop a superlattice detector. And for the purposes of this discussion, I'm just showing that, yes, you can actually tune things and get this is measured spectral response data. It's not quantified relative to an absolute. And so that's why it's in arbitrary units. But nonetheless, it's experimental data showing that you can have this push button tunability. Okay, so what are the takeaways? We can really engineer these dispersions. We can also switch these dispersions. We can do all of this in a system that scales the right way with devices. So let's go ahead and do it. And so what my group's going to be working on is that we're going to be designing not just materials that have polaritons by themselves, but actually making thermal metamaterials. And so we're thinking about the implications of hyperbolic materials, of topological approaches to designing these polaritonic thermal systems. So effectively taking the work that, of course, goes on every day here in the Berk, looking at how to leverage these phenomena in optics and nanophotonics, but applying it to a thermal problem. And we're going to do that by approaching the problem by really cultivating our dispersions from Maxwell's equations rather than kind of the classic dynamical equations of thermal transport. And then effectively what we want to do is demonstrate that there is this hybrid channel between radiation and conduction. So let me just explain, just because we're a community, here are some of the tools that we'll be using in my group, because of course a new professor means a new startup, which means new tools in the system. So we'll be bringing online a VTech spectral imaging system. And so this allows us to take Raman photoluminescence, photocurrent mapping measurements down to, it's a diffraction limited spot size, but we've been able to image at Sandia down to about 200 nanometers. We can couple in, we can also do that transient, we can do that cryogenically all the way up to 600K. We'll also be adding on to our ellipsometric capabilities here by bringing in an infrared variable angle spectroscopic ellipsometer, and then kind of working with Professor Zhu's group, I'm hoping to expand the wavelength of their FTIR microscope. So the message is we have the tools to measure the thermal transport in this building, to measure these dispersions, to measure the optical properties. And then also we have experience in my group of working with 2D materials and fabricating thwant devices. And so, those are the toys, but also as I kind of wrap up here, I want to want to discuss, you see a lot of spectrometers on here. And so that's the other thing that we'll be working on quite a bit in my group is really leveraging Polaritons for spectroscopy and really trying to change the way that we do spectroscopy in general. So this is just a little vignette, but I really see three problems in spectroscopy. Number one, they're still the size of suitcases. Number two, they're general. We don't really make spectrometers for a single purpose because they're big and expensive. And then the third problem is when we use photons for spectroscopy, we're really stuck at the gamma point. We're stuck on the gamma, or we're stuck on the light line. And so we want to get off of that if we want to see more of the Brillouin zone as we kind of probe these materials. And I think Polaritons give us a way that we can do that. And so the way that we're going to approach that is by combining metasurface filters that are very, very narrow. That's why we use Polaritons. Most FTIRs that are working in the mid and the long wave, if we think about what the passbands are, the Q factors for the passband for an FTIR are on the order of 100 to 125. That is very doable for a lot of the phanoresonances in dielectric materials. I think we can combine those metasurfaces with some kind of AI-informed and compressive sensing spectral reconstruction algorithms so that we can actually miniaturize everything and get it on a chip and actually make it to order. And then the other thing I think that we can do, and this is probably separate to the chip, is really think about purposely designing metasurfaces to analyze materials using Polaritons such that we get off the light line. And so we have more momentum and can examine more of the Brillouin zone. And so I always think about the fact that to get off the gamma point to look at phonon physics, I typically have to go to Oak Ridge and look and use their neutron source. I'd like to get off the light. I'd like to be able to do that in my lab. Are we going to replace the neutron source? No. Can we maybe get something that everybody can use in our lab that gives us a little bit more information for a lot less resources? Yeah, I think we can do that. So, just as I'm wrapping up, I appreciate the opportunity to be here and really just introduce myself to this community. One of the reasons that I came here was to work at Burke. I've been a long admirer of the work that's being done here, the collaborative nature. And so the chance to get to introduce myself and just say, hey, we're the Specir group. We're a light lab that uses a lot of infrared physics to create thermal spectroscopic and sensing solutions. And we're excited to get started. And if you have students that you think would be interested or colleagues that you think have good fits, we're looking to hire students. And so with that, I'm happy to chat, and I look forward to getting to meet all y'all as in person. So thanks a bunch.